If it's not one second, sure. It just comes to the road is the thing. One day. There's story looking about. I think I heard that. I don't think one was near stable. I was pretty good at it. Yeah.
Oh, has no one popped that open yet?
I'll be honest, I think that they're. That's it.
Running in progress. That's enough.
All right, welcome to week 2, everyone. Hope you had a good weekend. We're going to start off with a series of lectures throughout the day, with more and more time later in the week, so you can actually produce something to show your colleagues on Friday. But today, this morning, we're going to start off with a short research presentation by Martine. So let's give her a round of applause.
Hello, captive audience. So I'm going to open this up by saying most of this is going to be a lot of background and motivation, really touching on something that's been mentioned in the summer school, but kind of shoved off as this nebulous thing. Intrinsic red noise, it's kind of a nebulous, I would say, splinter in our side. It's not the biggest of field for millisecond pulsar timing, but it does exist, and I'm going to get into that a little bit. And it's definitely one of our more, to me anyway, but I might be biased, one of our more interesting sources of noise. This project is very much in its infancy stage. I just started it, but I'm very excited to talk about it. So this is my yap session about that. So through tackling the intrinsic red noise problem, we can learn a lot about neutron stars. And I can say that, and I'm sure you believe me, but let me show you why. First of all, please work. It's not working. All right, that's fine. There we go. What is intrinsic red noise? By definition, it is a stochastic and sustained deviation in spin phase. This is not to be confused with glitches, which are going to be sudden jumps. And those are interesting in their own right for neutron star physics. But whenever we have this sustained and stochastic smooth deviation, this is going to be what we're going to call spin noise, timing noise, intrinsic red noise. 3 names for the same thing. If you ever see spin noise, timing noise, IRN, or intrinsic red noise, same thing. And I might have a bad habit of using them semi-interchangeably throughout this. I'm going to try to stick to IRN or intrinsic red noise, but I might not be perfect. We know that the only way for the spin down of a pulsar to be changing is for something to be happening within the local pulsar regime itself. This is, of course, very interesting to neutron star physics, which we famously do not understand. When we see it in our residuals, this is what it looks like. This is a famous one, B1937 plus 21. It is included in our PTA, and it has a lot of intrinsic red noise. So after we come in through here and we put in our very long model, I took a look at the PAR file for this thing. It is long. We still have this unexplained sinusoidal behavior and this sustained stochastic deviation from what we would expect. So this is what it looks like. And it does exist in some millisecond pulsars. 1909, for example, famous for being a good timer, has like none of this. So who and where? So how many of you guys have seen this diagram before? Okay, not everyone. This diagram has a funny name because I have the humor of a 12-year-old. This is a period and period derivative plot, or a PP dot for short. And it is just going to be putting the period derivative plot of pulsars on this graph. Down here in the green, we have our tried and true beloved millisecond pulsars. You can see very little deviation, very small period derivative. They're very stable down here. Up on the top, on the other side, these are our magnetars. We don't have a lot of these in our collection. Hopefully we can change that so we can study them more. But these are young and chaotic. They're known for throwing tantrums all the time. And that's a very fun avenue if you want to look at FRBs. Anyone could talk to me about those as well. In the middle here, this big blob of blue, this is pulsars that are anywhere from middle age to ancient. The only thing that distinguishes the millisecond pulsar from some of the most ancient members of these canonical pulsars is if they've had their white dwarf snack yet to spin up and become our beloved stable clocks. While we're looking at this, I really want to highlight these gray bands, which might just be fading in the background, but are actually going to be the subject of this talk. Those are showing the amount of timing noise variability, or the RMS of timing noise, or intrinsic red noise. Again, interchangeable. MSTs have very little, but it's not insignificant for all of them. Magnetars are of course going to have the most. They're going to be the most chaotic, most unexplained, and canonical pulsars take on a whole host of values. This region in particular is one that's very interesting to me because there seems to be I would think there'd be a common source of timing noise going on here, and we will get to that later. Is this significant for us? Does it matter for us? Well, this histogram is going to kind of explain that. This is a proposed amplitude. Let me put an asterisk on that proposed. The proposed amplitude of intrinsic red noise in comparison to the gravitational wave background amplitude. For millisecond pulsars, most of them, the gravitational wave background amplitude is much more than or more by some degree, not necessarily much more of the amplitude of red noise for that pulsar, but not all. Of course, all of this is all of that over there. So we still have some fraction by this estimation of millisecond pulsars that do contend with intrinsic red noise as a factor in their data. And I really want to throw a really big purple asterisk on this. This is a shape that we will see later. So I want you to kind of put in your mind that this is one proposed model, and we'll get to that in a moment. So what is it? That is a fantastic question. That's the fun part. We don't really know. We have ideas, but the problem is we don't understand neutron stars. We can characterize the data, but we don't understand it. Don't know why that did that. Possible theories of its origin include non-stationarity in the pulsar beam. For some reason, we don't really have a good example for that, but that would explain what would be happening. Again, that would be something probably going on in a local magnetosphere or in the neutron star crust. Could be changes to the interior of the neutron star that are connected to the superfluous crust on the outside. That could be causing changes, or just changes to the interior of the neutron star that are changing its moment of inertia, and therefore that would affect the spin down. It could be due to magnetosphere state switching. It could be due to asteroid belts surrounding the pulsar. This does kind of have a specific case, but we can get into that later. The theories haven't really been updated since the 70s. People had some ideas, they put them out there. That's kind of where we are, and no one's really been able to make much more progress on it ever since. Because I also don't think many people have cared. So how do we characterize this? Well, it's a stochastic variation, so we can characterize as a damp random walk. Whoop-de-doo. You can also go one step further and do 2 damp random walks in frequency derivative, as well as having discrete jumps, multiple of them, in frequency derivative, and spin phase. That's a simple model, isn't it? That seems like that's definitely physical. You also can do a power law. And this would be expected because it behaves as a sinusoid in time space, so it would be a power law in frequency space. Now here comes that asterisk. Looks a bit faded up here, but this is the asterisk I'm going to put in. Someone did this. A very well-known paper, Shannon Cords, names you probably have seen around a lot of noise analysis papers. Shannon Cords in 2010 did a maximum likelihood analysis to fit the indexes of a power law of timing noise across populations. They did 2 maximum likelihood analysis, one over just the canonical pulsars and one over a joint data set of canonical pulsars and millisecond pulsars. They did magnetize 2, but it wasn't fruitful. So this is that power law that they characterized. this is just a coefficient, this is just frequency, and that's frequency derivative, and T is time span. I'm not going to be, this is pretty simple. I think we can take a look at this. Now, this is the main output of that work. Now, I can look at this and go, wow, ooh, ah, graph. But there's a lot of weird code in here. So I'm going to break this down so we all can agree what we're looking at, because understanding this plot is necessary for the motivation for what I am doing. On the left, over here, we have the maximum likelihood analysis done over millisecond pulsars and canonical pulsars. On the right is the canonical pulsar set only. On the x-axis, you have their model prediction of the root mean squared of IRN, or the time or the variability of that intrinsic red noise. On the y-axis is your measured values. Now you'll notice these little C's up here. That up here, it would be an overpredicted regime, and down here would be an underpredicted regime. So, furthermore, one last little piece of this puzzle. These squares, those are millisecond pulsars, circles and dots are canonical pulsars, and stars are magnetars. So that is how we decode this graph. Now I want to take a look at it. What did they find? How did their model do? Let's first take a look at our tried and true beloved millisecond pulsars. How'd they do? In the joint data set, it's okay. It has a lot of spread. This is the 1 sigma line. This is the 2 sigma line. It's kind of all over the place. I wouldn't say, to me, this is indicative of much more that you can fit a straight line through a cloud. On the just the canonical pulsar side only, we see it very much is not characterizing the timing noise in millisecond pulsars very well at all. How's it behaving for canonical pulsars? There's much more of these guys, so they're going to weigh down the data set. But they both fail to characterize this region over here. So there's this large deviation from the line in canonical pulsars that is just not considered. It's just they're statistical outliers, and their timing noise is not characterized by this at all. This region it's fine. Like this is a pretty good, I think, fit for the timing noise for canonical pulsars in this region. However, this is not accounting for or explaining in any way any of the timing noise we see in any other type of pulsar. And this method completely breaks down when it comes to magnetars. But again, also our data set for that is not as large for this, so it's going to be really difficult to compare those. So where do we stand? I'm putting in my project a new perspective going forward. This power law is treating all sources of intrinsic noise as if they were the same. One spectral index to rule them all, or 3 to rule them all, but it's not allowing for there to be multiple types. Remember how I told you about that very complicated model with the 2 random walks and 3 sets of multiple discrete jumps? That paper did this because they were considering multiple sources of intrinsic red noise to be at play in any given neutron star. So we have a lot of strong implication, especially by the Shannon and Ford's work not being able to fully describe it, that there are multiple processes that can co-occur. Also, they only did population modeling across classifications. So they said everything that we humans consider to be canonical pulsars, we're going to set those as the population, and we're going to treat them all the same. We might not necessarily be able to do that. We're also going to treat all millisecond pulsars as exactly the same. There are a lot of millisecond pulsars that are not good timers that we do not include in our data set for a reason. So it's difficult for us to set these classifications that we as man have made and justify our physics on them when there might be more to the story. As we all know, there are 88 types of variable stars. There's a lot that can go on in these chaotic physics laboratories. So we should be doing population modeling across multiple subpopulations instead of just these classifications. I also would then expect there to be comorbidities in the data. And I can't find a less morbid word for this, but just other things that might occur, whether it is other noise parameters, location, anything else that's going to be in that lovely car file, other things that might occur that might indicate some different type or subclassification of intrinsic red noise. And we should be looking for those. We're going to attack this with hierarchical modeling. So the strategy for this is going to be specific in the questions we're asking. And this is a change to this project that actually came from talking to Thankful while here. This is because data availability is hard. We have a great repository in a graph for millisecond pulsars. This is wonderful. Canonical pulsar data is kind of all over the place. Magnetar is even harder to find. So by being specific in the questions I'm going to be asking, I'm going to be mitigating data accessibility issues. Oh, this is working. Furthermore, it will also mitigate the results favoring one more type of intrinsic red noise over the other, like we saw with the maximum likelihood analysis with the canonical pulsars. That was completely weighted in one type of timing noise that's favored. And who's to say that there's just a large population of neutron stars in one regime that just have a specific type of intrinsic red noise that is going to be less common to neutron stars of a different type, of different age, of different circumstances. These objects have a lot of variability. I'm also going to focus this project on very much differentiating those types of timing noise. Ultimately, the thing that if everything goes right and everything goes well, I will be able to make an argument about the intrinsic red noise generation mechanism. Right now, we have ideas, and that's how every paper on this starts. This is what it could be. But we have all of this timing data just lying around. It's just waiting for us to ask the right neutron star questions. We've asked a lot of gravitational wave questions, and this has been really good. But we have so much data. We just need to ask the right questions. And I think we'll be able to make an argument for generation mechanisms and have one in favor of the other, or discuss the circumstances where one is more likely to occur. Through this, we'll make a more descriptive model of intrinsic red noise. That power law is a great first pass. It can describe some of them, but it does not completely describe everything. Furthermore, it does not offer understanding into the neutron star physics that are going on inside of the star. And that is of great interest to us as a society. How am I going to do this? Well, for each specific question, I will construct a data set of interesting neutron stars for that. I will then do a modern noise analysis on this. Luckily, I am in the noise group, so I have access to the preemptive noise experts 10 feet away, if even more like 5. And then on each one, I'll do a hierarchical model to kind of see what is the probability of that spectral noise index per this population. I did this twice on accident. Oops. And that's my project.
Questions from Martine?
Yeah.
With the period dot plot, for the distinction between slow and fast millisecond pulsars,
Yes.
I'm not aware that was, I know obviously the periods, but like when we're doing pulsar timing arrays, do we make this distinction?
Yes. Pulsar timing arrays use fast millisecond pulsars. Because if you notice on that graph, the slow millisecond pulsars will have more timing noise.
Right.
They are less that implies they're less stable clocks because that spin down derivative is changing a lot more. Yeah.
Any more questions for this morning? If not, you can catch Martine anytime this week. More questions? Second again. All right, up next, we've got a tag team lecture. Andrea Mitridate is a Royal Society University Research Fellow at Imperial College London, one of the co-chairs of the New Physics Working Group, and an all-round expert on new physics sources of gravitational waves. And Andrea, I think we'll hand over about halfway through to Kristen, who we met last week, who's an NSF Ascend postdoctoral fellow at Caltech and UT Austin, and an expert in beyond GR theories of gravity. I'm trained by Leo Stein to call it beyond GR instead of modified gravity, but I know it's interchangeable. So I'll leave it to you both where you want to have the division between the two sets of content. But for now, I will pass it over to Andrea, and thank you again, Andrea, for joining and doing this.
Yeah, thank you, Steve. So hopefully you can see my screen and you can hear me well. So before I start, I know it's always a bit harder when giving a lecture remotely, but if at any point there is something which is not clear, feel free to stop me. I'll try to have
Andrea,
a look.
sorry, we're not hearing you.
You're not hearing me.
I wonder if there's a problem. Hold on.
Okay.
That'll be why.
Can you hear me now?
That's it. We got you. Yes.
Can you hear me now? Okay, perfect. So yeah, so I was just saying that it's always a bit harder when giving a lecture remotely, as you can tell. But feel free to stop me at any point if there is something which is not clear. I'll try to keep a look on the chat. So yeah, if you want to send a message or just speak up, I'll try to keep an eye out for that.
We can also start a thread Slack as well, Andrea. In case
Okay, yeah, I'm also happy to answer later on if you have questions on Slack. Yeah, that's perfect. Okay, so I think I can get started. I think over the last week, you have already learned that supermassive black hole binaries are a great source of gravitational waves on nanohertz frequencies. And despite the fact that we still do not have a direct evidence that they're produced in the background that we are starting to see in our data, they are the most likely candidate. And if that's the case, by using pulsar timing array observations, we will be able to learn something about the properties of these supermassive black hole binaries and their population. However, some of you may be wondering if there is anything else that we can learn from pulsar timing observations. And the goal of the next hour or so is to try to answer this question. Specifically, we will look at how we can use pulsar timing observations to learn something about dark matter, the very early universe, so anything that took place prior to recombination, and finally, the theory of gravity itself. So as Steve was saying, I will focus mostly on this, on the first 2 points on this slide, and then I will pass it over to Kristen that will tell us something about the last point. Okay, so I will start with dark matter. So what we can learn about dark matter from pulsar timing observations. And I think a good way to get into this topic is by realizing something that probably you already know. That is the fact that not only gravitational waves can produce signals in the TOAs. So probably you're already familiar with the fact that the radiation which is emitted by the pulsars before reaching us here on Earth has to go through the interstellar medium. And the interaction between these radio waves and the interstellar medium can produce chromatic perturbations in the TOAs that we have to model very carefully. Otherwise, we could miss whatever gravitational wave signal is in our data, or we could mischaracterize it. So this is a very important effect, which is not of gravitational wave nature. It's just due to the interaction between the photons and this interstellar medium. But you also know that both the pulsars that we time and us on Earth, we are all embedded in a dark matter halo. So we have evidences across a variety of scales that dark matter must be out there in the universe. And specifically on galactic scales, we have rotation curves that tell us that to explain the motion of stars in the galaxy needs to be embedded in a halo of dark matter. So you might be wondering if the propagation of the radio waves through this halo of dark matter before reaching us, these radio waves has to go through this dark matter field. If this propagation and the possible interactions of the radio waves with this dark matter field could produce a signal in our data, and if we can learn something eventually from our data about the nature of dark matter and this dark matter halo. And that would be something quite nice because we know very little about dark matter. So we know it's out there. We know how much dark matter is in the universe, and we know more or less how much dark matter needs to be within our galaxy. But apart from that, we know very little. And for example, we know almost nothing about the mass that this dark matter particle, if it's a particle, has to have. So if the dark matter is a boson, so a scalar or a vector or a tensor field, the mass of this dark matter particle can be anywhere between 10 to the minus 21 electron volts, which, if you're not familiar with natural units, this is roughly 10 to the minus 27, something like that, the mass of one electron, so very light dark matter particles, but can go all the way up to macroscopic scale. So the dark matter can be in the form of macroscopic objects like primordial black holes, and these have masses which are of order of a solar mass. So we know almost nothing about the possible mass of dark matter. And PTA can help us probe possible dark matter candidates in some of these mass range. And to start with, I will focus on the very low end of this mass range, this allowed mass range for the dark matter. And the dark matter candidates that live at these very low masses are called ultralight dark matter candidates. And they're characterized by masses which are well below the electron volt. And a peculiar property of these ultralight dark matter candidates is that they have a very large density within the galaxy. So we know what is the density of dark matter in the proximity of the solar system. This is roughly 0.4 GeV per centimeter cube. So if you know the energy density and you know the mass of the dark matter, you can compute the number density, which is just the energy density divided by the mass. And what you find is that the number density of these ultralight particles must be very large. So like in the room you are sitting in, probably there should be billions of these ultralight dark matter particles. And what's interesting is that when you pack such large numbers of particles within a finite volume, like our galaxy, you can start describing this ultralight dark matter not as a collection of particles, but as a classical field. So just like if you have a very bright source of photons, right, like a star, you don't typically describe the emission of the star in terms of individual photons, but you describe the emission in terms of classical electromagnetic fields. And the same you can do with these very light dark matter candidates because their number density within the galaxy is so large. So in this scenario, what you have is that the pulsars that we are monitoring and us on Earth, we are all embedded in this field of dark matter. And this field is not a static field, right? This field will be oscillating both in space and in time. And this is what you're seeing in this animation, right? This phi is the dark matter field, and it's color-coded according to the value of this field. And you see that there are these oscillations that are taking place both in space and in time. And in the lower panel, you're seeing the field value that is experienced by the pulsar, which is this green line, and by the Earth, which is this orange line. So you see that there are fixed spatial positions, so they only experience these time oscillations. Now, more precisely, the typical amplitude of these oscillations is set by the local density of the dark matter, which is this rho phi, and then the mass of the dark matter itself. Ignore for a second this phi hat. I'll go back to it in a second. The second important point are what is the scale of these time fluctuations? What is the frequency? And the frequency of these oscillations is set by the dark matter mass. So if you have a mass which is around 10 to the minus 23 electron volt, the frequency of these oscillations is around the nanohertz, which, as you might guess, it's quite convenient if you want to probe these fields using pulsar timing observations. And then you have also oscillations in space, and the typical wavelength of these oscillations for the dark matter around 10 to the minus 23 eV is around a kiloparsec, which is also kind of a coincidence. It's the typical, close to the typical separation between the pulsars that we're monitoring. Okay, let me go back to this phi hat quantity, which I haven't defined. So this phi hat is controlling the amplitude. Okay, the typical amplitude is common across all positions in space. It's given by this the square root of the density divided by the mass. But then at each point, you're going to have some modulation of this typical amplitude. So this phi hat at each point in space, it's a random quantity. And the value of this random quantity at different position in space will be correlated. So if you take 2 points in space, which are at a separation which is much smaller than the typical wavelength of these dark matter oscillations, the value of this phi hat is going to be tightly correlated. And this is what I'm showing in this case. You see these 2 points, the green and the orange points, are very close to each other. So the amplitude of the oscillations that they experience is going to be tightly correlated. Essentially, it's going to be the same. But if you take 2 points which are widely separated, so at separations which are much larger than the wavelength of the dark matter field oscillations, then these 2 phi hat quantities, which rescale the typical amplitude, are going to be essentially 2 independent random variables. So you can have a realization in which one of these observers is experiencing very large oscillations, while the other observer is experiencing very small oscillations. Okay, so this is the setup of these kind of models. So if the dark matter was in the form of this ultralight field, the radiation which is emitted by the pulsar before reaching us on Earth has to go through this oscillating dark matter field. So you might be wondering if these oscillations imprint any signal in the TOAs that we measure. So to answer this question, we can look at the perturbation of the metric, which are sourced by these oscillations in the dark matter field. And this is what I'm writing here in the left column. So ds squared, this is the metric. And you can see that these oscillations in the dark matter field produce a scalar perturbation to the time component of the metric, which is related to the value of the dark matter field. Here I'm throwing away some subleading terms, but if you're interested in the full-fledged calculation, you can look at this seminal paper by Klemensky and Rubakov. Okay, as a reference, on the right panel of the slide, I'm writing the metric perturbation, which is produced by a gravitational wave. So this is something that you have already seen probably last week. Here, the spatial perturbation to the metric is produced by Hij, which is the metric tensor of the gravitational wave perturbation, which has these 2 indices because the metric perturbation produced by gravitational wave has a quadrupolar nature, while for the dark matter, it's even simpler. It's a scalar perturbation, so there are no indices associated with the perturbation. But you can see that the form of the metric perturbation is quite similar. So it's not surprising that when you compute the TOA perturbation, which is produced by the propagation of the photon through the dark matter field, you find a form for the time residuals, which is very similar to the one that is produced by gravitational waves. So specifically, the time residuals are proportional to the difference between the value of the dark matter field square at the location of the Earth. This is the analogous of the Earth term, and this is this first term, minus the value of the field square at the location of the pulsar when the radiation was emitted. And you see it's a very similar structure to the one for the signal produced by a gravitational wave. Okay, so you can now take this expression for the time residuals, and you can plug in the expression for phi squared that I gave in the previous line. So you can take this expression, plug it into this one, and you find the final form for the signal that you expect to be produced by these ultralight dark matter fields. And this is a deterministic signal, so it's similar to a continuous wave signal if you want, and we can do a Bayesian search for this signal. So the parameters that would enter in this Bayesian search are one parameter for the amplitude of the signal, which is controlled again by the local dark matter density and the dark matter mass. Then you're going to have one parameter that controls the frequency of the signal, and this is given by twice the dark matter mass. And then you have 1 plus the number of pulsar phase parameters. These are this alpha E, which is the phase of the signal at the location of the Earth, and then you have this alpha A, which are the phases of the signal at each pulsar location. And finally, you have all these scale parameters, which are in general n pulsar plus 1 scale parameters, which have some non-trivial correlations among each other because as I told you before, depending on the distance of the pulsars, these scale parameters are going to be more or less correlated among each other. So we already looked for this kind of deterministic signal that could be produced by this ultralight dark matter field, both in the nanograph 15-year dataset and the European DRC dataset, so roughly 3 years ago. We didn't find any evidence for such monochromatic signals apart from a mild anomaly around 4 nanohertz, which I think it's also the same that appears in continuous wave searches. But the evidence was fairly low, so we only put upper limits on the local density of these ultralight fields. And these are these red lines that you can see in these plots. So in the plots, you can also see these horizontal dashed lines in both the nanograph and the EPTA plot. So this horizontal dashed line is telling you what is the value of the dark matter density that you expect to have in the proximity of the solar system. So if the totality of the dark matter was in this ultralight field, you should find a signal consistent with this local dark matter density. So you see that for the nanograph analysis, we were not able to reach this expected density value, which is unexpected amplitude value, if you want. But for the EPTA case, they were able to constrain values of the density which are smaller than the expected one. So essentially, they were able to say that the dark matter cannot be in the form of these ultralight fields, at least for masses which are between 10 to the minus 24 and 10 to the minus 23 electron volts. So you can also probably notice that in these plots, there are multiple lines. If you focus on the dark matter, in the nanograph plot, we have 2 lines which are labeled correlated and uncorrelated. And this is related to how we treat these scale parameters in analysis. So I told you that in general, these scale parameters have some non-trivial correlations among each other. But at least at the time we did this analysis, we were not able to model this multidimensional correlated prior properly. So we work in 2 simplifying regimes. One that is called correlated, in which we assume that all the pulsars and also the Earth are within one wavelength of this dark matter oscillation, such that the scale parameters are all fully correlated among each other. So you essentially have one effective scale parameter that controls the oscillation amplitude for all the pulsars and the Earth. And then there is the opposite regime, that is what we call uncorrelated. Here you assume that each pulsar and the Earth, each one of these observer is in a different coherence patch, so in a different wavelength of the oscillation of the dark matter field. So these scale parameters are completely uncorrelated. So you have NP plus 1 parameters that you can do inference over in your Bayesian run. In theory, if you wanted to be correct, you are never in any of these 2 regimes, right? At very low masses, when the wavelength of the dark matter field is very large, the correlated regime is more appropriate. At higher masses, where the wavelength of the dark matter field becomes smaller, the uncorrelated regime is more appropriate. But in between, you are going to be somewhere between these 2 limiting cases. At the time, we were not able to model this appropriately, but I think tomorrow, or definitely within this week, a paper is going to appear on the archive where we develop a formalism to properly take into account these correlations without having to make these simplifying assumptions. Okay, so this is just one example of a dark matter model that we can test using our observations. There are many more, okay? I cannot really go over the details of all these different scenarios that we can try to test, but I wanted just to give you a taste, right? So in the next few slides, I'm gonna go over very quickly some other scenarios of dark matter models that we can test using pulsar timing observations. And if any of these catches your attention, you can ask me at the end or stop me now and ask for more details. So the first one is still an ultralight dark matter model, but the difference is that these ultralight dark matter models, which so far I've assumed couple only gravitationally to photons and matter, in principle, they could have other couplings, right? They could couple directly to photons, they could couple directly to electrons, and so on. And what you can show, for example, if this dark matter field couples directly to photons or electrons, the oscillations in the dark matter field will transfer to, for example, the frequencies of the atomic clocks that we use to time the pulsar. So as the dark matter field oscillates, if this field couples directly to the electrons, for example, also the frequencies of these atomic clocks will oscillate, and this will produce a signal or a perturbation in the T waves. So what you can do is to look for these signals. It's a similar search to the one that I've just described. We didn't find any evidence apart for, again, this excess around 4 nanohertz, but we were able to set constraints on the value of all these couplings. So each panel in this plot, it's a different coupling. So you have a coupling to quarks, electrons, muons, photons, and gluons. Each one of these couplings will produce some perturbations to some frequencies of atomic clocks, or the moment of inertia of pulsars, which I haven't mentioned. But you can look for these signals and set constraints on these couplings. And you can see that the constraints that we were able to set for some of this coupling, for example, the coupling to the electrons, is stronger than other constraints that are placed using terrestrial experiments, which are shown with these other exclusion regions in different colors. So this is another property of this ultralight field that we can test using PTA observation. Another test of dark matter properties that we can do is by moving our attention away from our galaxy, but to the center of other galaxies. So if you assume that the background that we are seeing is indeed produced by supermassive black hole binaries, you know that the power spectrum for the background that is produced by these binaries strongly depends on how quickly this binary evolve, right? How quickly their orbit shrinks and they reach the PTA band. And you probably already heard during last week classes that this evolution is driven by gravitational wave emission, but also it's very important the interaction of these binaries with the star and the gas environment at the galactic center. But we also know that the galactic center is very rich in dark matter. So there is a high density of dark matter particles at the galactic center that can influence the evolution of these binaries, especially in some models of dark matter that predict a spike of dark matter density at the galactic center. So what you can do is to study how the power spectrum for the background, which is produced by supermassive black hole binaries, is modified when you change the density of dark matter galactic centers. And this is what was studied in this paper. So in this plot, you can see the power spectrum for the black hole binary reduced gravitational wave background. And now it changes when you increase the dark matter density at the galactic center. So you see that as you increase the density of dark matter at the galactic center, the power at lower frequencies is more and more suppressed because the hardening of the binary is dominated by this interaction with the dark matter field. You can also do some Bayesian analysis trying to reconstruct the properties of this dark matter spike at the galactic center, and this is what is shown in this plot. And finally, so far, or at least in the main discussion, I focus on very light dark matter fields, but surprisingly, PTAs can probe also the opposite mass range, so the very heavy ones. So for example, primordial black holes. So if dark matter is in the form of these macroscopic clumps of dark matter or these primordial black holes, these dark matter clumps will move around the galaxy. And what can happen is that one of these dark matter object can transit close to one of the pulsars that we are timing. And the gravitational pull of this dark matter clump can accelerate the pulsar. This will induce a Doppler perturbation in the TOAs that we can look for. Or this dark matter clump can transit along the line of sight between the pulsar and the Earth, produce a gravitational perturbation along the line of sight, the photons have to travel through this gravitational perturbation, and this will produce what we call a Shapiro signal in the TOAs. So if this transiting event at timescales which are smaller than the typical observing time of our observations, you can show that the signal that they will produce in the time residuals is a deterministic signal that is proportional to the observing time to the cube. So you can look for this kind of drift in the TOAs. So this is something that we did for the 15-year in physics analysis, and we didn't find any. So we were able to place some upper limits on the local abundance of, for example, primordial black holes, which is what you're showing here. So we were able to say, if dark matter is in the form of these primordial black holes, you cannot have more than this quantity in these given mass ranges. Okay, so this is a quick survey of some of dark matter scenarios that we can test using PTAs. There are some more that I couldn't cover, but this should give you an idea of the kind of dark matter properties and dark matter models that we can probe and constraints and hopefully detect using PTA observations. So this is, I think, a good time to pause just in case there is any question about the dark matter part, because then we will kind of shift to a bit different topic. Okay, I see someone moving in the room.
Hello, can you hear me?
Yeah.
Okay. I was curious for this primordial black hole kind of line of questioning. Can you say a little bit about how the mass of the primordial black hole connects to the frequency? Or I'm trying to understand the parameters for this kind of thing.
Yeah, so so it's not a periodic signal, so right, there is not necessarily a frequency per se. So the signal that I'm showing in this slide is deriving this specific limit in which the transiting event, so there is this primordial black holes, for example, transiting near one of the pulsar, the time scale of this encounter is much longer than the observing time. So over our observing time, the position of these black holes compared to the pulsar is changing very slowly. So you can do an expansion in T over T small over T observing time. And the linear and quadratic term, which in principle are there, are absorbed by the timing model. So what you're left with is this cubic term, which is a deterministic signal that you can look for. And the amplitude of this cubic drift in the TOAs is going to be fixed by the impact parameter of your encounter. So you can map this amplitude in the impact parameter and the mass of the primordial black hole, for example.
Okay, thank you.
Yeah, no problem. Okay, I don't see any message in the chat, so I will assume that I can move on. And as I was saying, we are gonna change a bit topic. So far, I focus on these signals which are not necessarily gravitational wave related. Now we go back to the gravitational wave signals that we all know and love. And I'm gonna talk about some scenarios which have attracted a lot of attention. And these are scenarios in which the background that we are seeing, it's not produced, or at least it's not entirely produced by supermassive black hole binaries, but instead by some source of gravitational waves in the early universe. So to put this into perspective, what I mean by early universe is everything that took place through cosmic history prior to the recombination era. So the recombination era is when the universe goes from being filled of electrons and nuclei to be filled by neutral atoms. So the electrons recombine with the nuclei, and everything or most of the matter in the universe becomes neutral. And this is a very interesting stage of cosmic history because we know that a lot of things have to take place. Here, for example, we know that there is this stage of exponential expansion of the universe. We don't exactly know what is driving this exponential expansion and how this expansion comes to an end. We also know that the asymmetry between matter and antimatter that we observe in the universe has to be formed during these early stages of cosmic history. So if you look at the sky, you see mostly matter. You might be wondering what happened to all the antimatter, and we know that this antimatter almost completely disappear prior to recombination. And finally, we know that the dark matter abundance that is out there was formed very early on because we know that the dark matter is needed to see the structures that we see in the universe. So this dark matter was formed very early on. Again, we don't know exactly how. So understanding what was going on during these early stages of cosmic history will help us understand something about dark matter, inflation, and all these interesting phenomena that we don't fully understand yet. The problem is that it's not easy to study what was going on in the universe prior to recombination. And the reason is that the main messenger that we use to study the universe, which are photons, it's not a good messenger for this stage of cosmic history. So if you want to study galaxies and stars, you can look at the electromagnetic radiation these objects emit, and hopefully that's enough to learn something about them. But the problem is that photons cannot really travel in the plasma that was filling this early universe, because as I was telling you about before, this is prior to recombination. So electrons and nuclei are not yet bonded together into neutral particles. Instead, you have this plasma of charged particles. So if you have a source of photons in this early universe, these photons will not really travel till us today, but instead they will scatter in this very dense plasma of charged particles. So if you look back in time in the universe, the furthest you can look using photons is the recombination era. So the furthest picture of the universe you can get is the CMB sky. Anything before that is kind of lost. And this is why the prospect of receiving a gravitational wave message from the early universe is very exciting, because gravitational waves, as we all know, interact very weakly with matter, which is also the reason they are so hard to detect. But in this case, it's quite convenient because they don't really care about this dense plasma of particles that was present in the early universe. If you have a source of these gravitational waves will just freely propagate and hopefully reach us today in a level that we can detect, and that will help us understand something about the source of these gravitational waves in the universe. Yeah, so that's why people were very excited about the possibility that the signal that we are seeing is produced in the early universe. And there is a plethora of possible sources of gravitational waves in the early universe. Again, I have like 15 minutes or so left, so I will not even attempt to cover them all. I will just focus on one, which is what we call cosmological phase transitions. So I picked this specific source of gravitational waves because you are all familiar with phase transitions. You encounter them in your everyday life. So, for example, every time you boil a pot of water, you are experiencing a phase transition. So water in the pot is going from a liquid phase to the gas state. And the reason why this happens is because when you fill the pot of water with liquid water, and the temperature is below the boiling point, the free potential for the water is going to have a minimum, which is for a density value which corresponds with the water liquid density. But as you heat up the water in the pot, the free potential will develop a new minimum, which corresponds with the density value for the gas state of water. And now the water in the pot can jump from the false minimum of the theory to the true minimum of the theory by nucleating this bubble of gas in the pot. And this is what you can see in this kind of slow motion picture. You see as you heat up the water, you start nucleating these bubbles. Now, since the pot is heated from below, in this specific case, the bubbles are mostly nucleated at the bottom of the pot. But if you could heat the pot homogeneously, this bubble will just randomly pop up in the water. And as you keep boiling the water, you will completely convert the water from the liquid to the gas state. Now, something very similar can in principle also occur in the early universe. Of course, the early universe is not filled with water, but it's filled with many other fields. So what can happen is that you have some field which is filling the universe, and the potential of the field has initially a minimum, which in this case corresponds to the origin. Okay, so the whole universe is filled with this field, which has a value which is set by the minimum of its potential. But the universe expands, and as it expands, it also cools down. And while cooling down, the potential for this field can develop a new minimum. And now, similarly to what the water did when you heat it up, this field can tunnel from the false minimum of the theory to the true minimum. And it's going to do so by nucleating these bubbles of the true minimum of the theory in the universe. And this is what you see in the simulations. You see that these bubbles pop up, they expand and they collide, and finally they convert all the universe to the new minimum of the theory. So what you can also see in this simulation is that initially these bubbles are nucleated and they're almost perfectly spherical. So there is no gravitational wave emission because of the spherical symmetry. But as they expand and collide, this spherical symmetry is broken. And when the spherical symmetry is broken, you can have some gravitational wave production. So part of the energy which is released in the phase transition can be converted into gravitational waves. Now, this is a very simple simulations that I coded up with Claude, so it's probably also wrong, but people have been looking at this way more carefully, and they have developed more accurate simulations that, for example, take into account that the nucleation and expansion of these bubbles doesn't happen in vacuum, but happens in the plasma that was filling the early universe. So as the bubbles expand in this plasma, they will also produce sound waves in the plasma. These sound waves will collide and produce turbulence. So what you can find is that during these phase transitions, there are typically three contributions to the production of gravitational waves: the collision of the bubble themselves, but also the collisions of the sound waves and the turbulence that is produced in the plasma. So this is a very complicated calculation. So you need very expensive numerical simulations to predict the exact power spectrum for the gravitational wave background, which is produced in these phase transitions. But the general form, a leading order, is quite simple. It's a simple broken power law. And the features of this broken power law are controlled by four parameters of the phase transition. First of all, the temperature of the universe when the transition took place, okay? So this parameter controls the location of the peak of the broken power law, okay? So if the transition took place around the GeV or 100 MeV, the peak of the spectrum is going to be in the nanohertz band. And as we will see in a second, this GeV 100 MeV temperature is quite, it's not a random temperature in the universe. Then, of course, there is the strength of the phase transition, so how much energy is released when these bubbles nucleate and collide. And this not surprisingly controls the amplitude of the power spectrum. So the more energy is released in the phase transition, the louder it's going to be the gravitational wave signal. And then you have the typical size of the bubbles when they nucleate. And this controls both the location of the peak and also the amplitude of the signal. And finally, you have the velocity at which these bubbles expand. Now, predicting the value of this velocity, it's a whole business. and it's very complicated. In general, it depends on both the strength of the phase transition, but also the strength of the interactions between the bubbles and the plasma in which they expand. This is very model dependent, depends on the details of the specific particle physics model that you're considering. Typically, in our analysis, we work in the simplifying scenario in which this velocity is essentially the speed of light, right? So you're assuming that these bubbles reach what is called a runaway regime, in which the bubble expand at the speed of light. This is typically true if the interactions with the plasma, between the bubbles and the plasma, are very weak. So there is not much friction that is slowing down the bubbles, or if the energy released in the phase transition is very large. Okay, so I told you about essentially the amplitude and location of the peak. What about the slopes of this broken power law? So at low frequencies, you can predict on fairly general grounds that the slope should be f to the cube. So the low frequency part, the strength is rising like f to the cube. But the high frequency tail, again, is fairly model dependent. So typically what we do is to leave the slope of this high frequency part of the spectrum as a free parameter. So then you can do inference. So you can write a template for this power spectrum that depends on these parameters. And you can do a Bayesian run and trying to reconstruct the values of these parameters. And this is what we did in the 15-year analysis. And these are the posteriors that we get. So you have two set of posteriors on this plot. The blue one are assuming that the totality of the gravitational wave signal that we see is produced by a phase transition in the early universe. And the red posteriors are assuming that the signal that we are seeing is some superposition of supermassive black hole signal and a phase transition signal. For both these analyses, you can see a couple of interesting things. First of all, the temperature of the transition is around 100 MeV, which, again, as we're going to see in the next slide, it's quite interesting. And secondly, you can see that the amplitude, so this alpha, is very large, it's close to 1, meaning that the amount of energy that was released in this phase transition was comparable with the total energy density in the universe at the time of the transition. So this must have been extremely loud and strong phase transition if you really want to explain the amplitude of the background that we are observing. Now, you might be wondering, okay, this seems very exotic scenario. Why should we have a phase transition in the universe? Well, actually, it's not that exotic. So we know that at least two phase transitions had to take place in the early universe. First of all, there is what we call the QCD phase transitions, during which quarks and gluons go from being free particles in the plasma to recombining into protons, neutrons, and other hadrons. And the temperature at which this phase transition takes place is, interestingly, very close to the temperature that we need to feed the PTA signal. So it's around 100 MeV. Unfortunately, within the standard model, there are simulations that predict that this phase transition is not first order. And by first order, I mean, it doesn't happen through the nucleation of this bubble. So a phase transition can be first order or second order. If it's first order, this transition of phase happens by nucleating this bubble, and you can have gravitational wave production. If it is second order, you don't nucleate bubble, the universe just slowly transitions from one vacuum to the other, and you don't have any gravitational wave production. So within the standard model, we think that the QCD phase transition is second order, so you don't have, or you don't expect a gravitational wave production, but there are proposed modifications to the standard model that will make this phase transition first order, which will give you a gravitational wave signal. And finally, a second phase transition and we need as to take place in the universe. This is higher temperature, around 100 GeV, is the transition in which the Higgs field acquires a non-zero value in the universe. gives a mass to all the particles of the standard model. So you see that these phase transitions that seem very exotic are not that much exotic. We know that at least two of them have to take place in the early universe. There might be more, especially because many theories of baryogenesis require a cosmological phase transition of the first order to take place in the early universe, and you might have gravitational wave production associated with that. Okay, so this is just one possible source of gravitational waves in the universe. There are many more. I will not discuss the details of these other sources. I will just essentially give you the names so you can orient yourself when you look at these new physics papers. So people went wild with possible ideas. So you can essentially choose your favorite model or source of gravitational waves in the early universe. People look at generation of these gravitational waves during inflation, right? So you can have production. Actually, we know there is production of gravitational waves during inflation. In the standard inflationary model, the amount of gravitational waves which is produced in the PTA band is too small to be detected, but you can have no minimal model of inflations in which the spectrum has a blue tilt, so the signal in the PTA band becomes detectable. Then you can have these models which are called scalar-induced gravitational waves. Here, the idea is that in the plasma of the early universe, you have large density fluctuations in the plasma of very small scales. People came up with these models because they wanted to see the formation of primordial black holes. So you have these very large density fluctuations on small scales. Some of them collapse into a primordial black hole, and that could explain the dark matter density. But what also happens if you have these very large density fluctuations is that you have some associated gravitational wave production, and that could explain the background that we're seeing. Then there are phase transitions, which is what we just discussed. And finally, there are cosmic strings, which are these defects in field configurations, which are formed during phase transitions. These strings form closed loops. The loops oscillate, and these oscillations can source gravitational waves, again, in an amount compatible with the ones that we are seeing in our data. So, as I promised, this was a flash overview about other possible sources. But yeah, if you have any question, you can ask also, because this was my last slide. So if you have any question before I pass it over to Kristen for the Beyond GR test, feel free to ask.
Okay, thank you very much, Andrea. If people have questions, they can ask now. It's probably easiest to go up to the meeting now if you want to ask that, or if you'd rather do it asynchronously, you can post your question in the Slack. Any questions right now?
Hey, can you hear me?
Yeah.
Okay, cool. I had a question about the bubble analogy for showing us the phase transition from the early universe. Would that not like, does it fundamentally change once we've undergone the phase transition, fundamentally change how gravitational waves propagate in our universe? Like how in the water analogy, how once it's undergone phase transition, right, the bubbles no longer appear because the phase does not propagate the same, the bubbles can't propagate through that new phase.
Typically, they can, right? The gravitational waves don't really care much about the field value in the universe. They can still freely propagate. So typically, you don't have a change in how gravitational waves propagate. Also, mostly gravitational waves experience only one of these two phases, right? Because they're formed when the phase is changing. So they essentially just experience the new phase, the new vacuum of the theory, which is the one that you get after the phase transition. So I might miss some exotic model, but I would say that typically you don't have a change in how gravitational waves propagate in the new phase of the theory.
Okay, cool. Thank you.
Anything else for right now? Okay, if it's, still a question you're trying to phrase in your mind, then I recommend going to the slide later on and posting a question for everyone. Let's give him another round of applause. Thank you very much for your time, Andrea. And
No worries.
now, Kristen's time. Kristen is back and going to give us a great talk on, I guess.
Beyond GR. We'll get there. Yeah, so I just wanted to start with a little joke, I guess, because I'm a new mom. I cannot tell you how many people have recommended this wonderful book series to me. It is very cute. I have read it. It is actually fairly accurate considering the level of the language. But it was pointed out to me that given the research that I do, what we really need is a beyond general relativity for babies. So I'm gonna give you a little bit of that today. And it's a little bit updated. It's really for students probably. Oh, good. The animations are super slow. Cool. Well, yeah. So this hopefully will be at a very introductory level of like why we go beyond GR, how we go beyond GR. I've included some links to review papers and that kind of stuff for you to learn more. But we're not doing heavy math today like we did last week. Okay. So I think we can't have a conversation about going beyond GR without acknowledging and understanding that GR works really well so far, right? So since its inception in 1915, GR has passed every single test we've set before it. And there have been a lot of them. There are over a century of tests and verified predictions of GR, enough to fill a whole book like that one, and certainly more than I could cover in the time that we have today. So I'm just going to briefly talk about a few of the very famous tests as examples. I would recommend this book. It was co-authored by my PhD advisor in Clifford Will, and it's written at the popular science level. So it's like a fun, easy read that gives you a little bit of the history of tests of GR. But anyway, today, so a couple examples. GR was able to explain the precession of the perihelion, or the point of the orbit that is closest to the sun of Mercury. And this was a phenomenon that had baffled astronomers for over 50 years by the time of its solution. So Newtonian gravity can predict the orbital motion of planets within our solar system, where gravitational fields are relatively weak, to such high accuracy that a deviation from the predicted orbit of Uranus was enough to indicate the existence of Neptune in 1846. However, when astronomers examined the orbit of Mercury, they found that the perihelion was precessing at a higher rate than expected. And they actually predicted that there might be an extra planet between Mercury and the sun. They were so confident that this must exist that they named it Vulcan preemptively. There is no other planet there. GR was able to reconcile this discrepancy between the prediction and observation with incredible accuracy and without disrupting theoretical agreements with the observation of other planets. So that was one of the first major successes of GR. In 1960, the gravitational redshift of light, wherein light loses energy and shifts to longer wavelengths as it climbs out of a gravitational potential well, was measured by Pound and Rebka. Here, oh, it didn't update. Oh my goodness, the animations are so slow. Not sure how to make that better.
Sorry, the Wi-Fi.
Yeah, let me stop sharing for one moment and see if I can fix that problem. I'm on ED-ROM, but it's not very fast.
Make it available offline and down, so.
Yeah, these are just on my laptop. But okay, we're on a new Wi-Fi. Let's see. Hopefully that will be faster. Okay. Great. So this is Glenn Repka at the bottom of the tower they used for this experiment. They did this in the tower at Harvard back in 1960. So that's kind of cool. And as we've talked about, as we've talked about many, many times over the last week, this binary pulsar observation provides a fantastic test of general relativity. So if GR works that well, why should we continue to test it? Well, fundamentally, the goal of science is to predict and verify, right? We don't want to just assume that a theory is true. We need to test it. We need to check. And we need to do this at multiple scales, right? Or across multiple regimes. So I'm going to follow the argument that's laid out in Nico, Javi, and Kent's review paper on Beyond GR in both ground-based detectors and PTAs. But in that paper, they go through sort of what these different regimes are. They do it by defining what they call the compactness. So it's just like the characteristic mass of the system over the characteristic length scale of that system. And they also talk about a characteristic velocity of the system. So like, what are the speeds that matter for this system? Everything in geometric units. So first, they talk about the weak field regime. So this is where the compactness is much less than 1, the velocities are much slower than the speed of light, and this is what we see in our typical solar system observations, right? So here, gravity is relatively weak. Next, we have the strong field regime. So this is what we're talking about when we talk about like binary pulsars that are widely separated. Those objects have really high compactness, but they're still moving at relatively slow speeds. And then finally, we have the extreme gravity regime. So this is like specifically compact binary coalescences, especially when we're getting close to the merger. Things are moving at significant fractions of the speed of light and very, very compact. Okay, so we had lots of tests in the solar system regime in the 70s and 80s. These are all laid out in the review paper by Will. Oh, and I will post these slides after, and all of these papers, not quite all, but a lot of these papers are linked. So you can just click on the link, it'll take you to the paper. Right, so there were a lot of tests in the solar system in the 70s and 80s. Our tests with binary pulsars really start in the 70s. But we weren't able to start tests in this extreme gravity regime until we really had this first direct observation of gravitational waves, which was just a little bit over 10 years ago in ground-based detectors and even more recently in PTAs, right? So in this regime, there are a whole bunch of new opportunities. There are a lot of new things that we can do to test GR. Okay, so hopefully I've convinced you that it's worth continuing to test GR. Why might we want to propose theories that go beyond GR? Well, GR is a beautiful theory, but we could be missing something, right? And as one example, we do not yet have a fully consistent theory of quantum gravity. So even though quantum mechanics is another incredibly well-verified and well-established pillar of modern physics, we can't get general relativity and quantum mechanics to play nicely together, right? And several attempts to unify these two theories have been made, but it's not clear that any of those attempts have gotten to the right answer. So for this and several other reasons, there are all kinds of different modified theories that are proposed to answer different open questions in physics, right? Sometimes we see an open question in physics and we say, maybe I can answer this by adding a little something to gravity. Okay. So I think to test or modify GR, we really want to try to understand why it's so special. So I'm going to try to give you a little bit of a breakdown of that. But we're going to try to do it somewhat simply. So first, I want to start with the action in general relativity, because this is really useful when we're talking about different theories, to be familiar with what the action looks like. Last time, I just gave you the Einstein field equations, but I want to get us used to this concept of like working from the action to get all of the stuff we need in a particular theory. So this is often called the Einstein-Hilbert action because Hilbert postulated the form of the action. It's actually very simple to write down. That's it. Okay. There we go. That's it. One line, one term, right? So we have an integral over the 4 dimensions of space-time. We have that square root of minus g factor, where g is the determinant of the metric. And we have that r, where r is our familiar Ricci scalar from last week. Okay? To get from the action to the field equations, hopefully you remember from some classical mechanics course that the action is the integral of the Lagrangian, and to find the equations of motion, we want to extremize the action, right? So we're going to set the variation of the action to 0, and from there we can do some algebra, we can do some integration by parts, so we can get the Euler-Lagrange equations, right? In field theory, we're going to do something similar. Again, we want to extremize the action, but now we're going to vary it with respect to a field. In the case of GR, the field we care about is the space-time metric. So we're going to vary the action with respect to the metric. Okay, so here's that action again. Obviously, that square root minus g term is going to depend on the metric because it's the determinant of the metric, right? R is hiding a factor of g mu nu times r mu nu. Let me see. Yes, there we go. And so both of those are also going to depend on the metric. So we've got 3 terms to deal with here after a lot of algebra that we do not have time to go through today because it would just take way too long. But I did post some notes on this for you on GitHub. You can also go through Carroll chapter 4. He does this. There's a link to his online notes there. But after a lot of algebra and work, we can get back to the Einstein field equations that we talked about last week. Great. Okay. And I do recommend that you try working through that yourself. It's worth doing at some point. All right, but what makes these field equations so special? Well, there's this special mathematical theorem that was proved back in the 70s by Lovelock. It was actually proved in a more general spacetime of dimension d, but he specified this to 4D spacetime and was able to show that the Einstein tensor there, this a g mu nu, plus a constant times the metric, is the only symmetric, divergence-free rank 2 tensor we can construct from just the metric and its derivatives up to second order. That was a lot of words. We're going to go through it in a little bit more detail in a moment, okay? But this corollary of Lovelock's theorem is really important because it shows that GR is unique. Okay, so not only is general relativity a good theory, but it is the unique metric theory of gravity in 4 dimensions under the following assumptions. So first assumption is that the metric is the only dynamical field. We have no torsion, we have no additional fields. So if you think back to what we did last Monday, we started with the spacetime metric. From there, we were able to construct the connection, which was just a function of the metric and derivatives of the metric. From the connection, we could make the Riemann tensor, which is just a function of the connection and derivatives of the connection, right? So now we've got a function of G, derivatives of G, and second order derivatives of G, right? From the Riemann tensor, we get the Ricci tensor, Ricci scalar, and we can get back the Einstein tensor. So we have at most, so we have only the metric as our dynamical field, and also at most second order derivatives of G in there. The third assumption is that the field equations depend only on the metric and its derivatives at a single point. We call this a local theory. And finally, the theory is diffeomorphism invariant. It holds in all coordinate systems. Okay. All right. So once we understand that GR is the unique theory under these assumptions, anything we do to try to modify GR is going to have to break one of those assumptions, right? So one of the nice ways that we can think about motivating modifications to GR or beyond GR theories is to break one of these assumptions at a time. It's also a nice way to test the theory, right? I can break a particular assumption and see if any of the signatures of breaking that assumption show up in the real world. So first, if we want to break this assumption that the metric is the only dynamical field, we can consider other fields. We can add a scalar field, a vector field, another tensor field. Or we could have something with torsion. If we want to assume that the equations of motion contain, we can allow higher than second derivatives of the metric, in the field equations, right? So that's breaking that second assumption. We could give up locality. And there was another assumption on the previous slide that wasn't in the list, but it was highlighted in blue. We were assuming we were working in 4 dimensions, right? So another thing that we can do is we can try to work in a higher dimensional space. So these are all things we can do to move to a beyond GR theory. Now, some theories will break more than one at a time, but I think this is a useful way to think about modifying GR. Okay, so by this point, we have a veritable zoo of modified theories of gravity. We've been doing this for a long time. Alternatives or beyond general relativity theories were proposed basically all the way back to right after general relativity was proposed. So this has been happening for a while. I'm going to show you some of them organized by the assumptions they break from the previous slide. This is basically just going to be a list of a lot of theory names. I don't expect you to understand what any of them are. The point is more to give you a bird's eye view of this really complicated landscape. Okay. So first we could consider other fields, right? We could add new field content. We could add a scalar field or a vector field or a tensor field. We could allow higher than second derivatives of the metric in the field equations, right? We could work in a higher dimensional space, or we could give up locality, right? So that's a mess. There's a lot of them, right? All of these modified theories that are up here so far modify the action in some way, and from there we can get the field equations and then figure out what deviations should show up in nature. We could instead assume that gravity is an emergent property and not something fundamental. There are also some approaches like that, but I have no experience with these theories, so I'm not the person to ask about them. In fact, in the 7 or so years that I've been working on tests of GR and modified gravity, I've only studied about 2 of these in any level of detail. So I think that just gives you an idea of the scope of this problem. There's a lot out there. And then this is just another nice graphic that I like that organizes some of the modified theories into what new things are there and how they can be constrained. There's a nice paper there you can check out if you want to learn more about that. But basically, all of this to say, we have like infinitely many possibilities, right? We can always add something else or more terms to the action. Of course, any new theory that we write down had better satisfy every test to date, which is hard to do because there's a lot of them. You don't want to be writing something down that obviously violates an experiment we've already done. But still, with so many possibilities, I think we have to ask the practical question of how do we even decide what to test? Okay, well, there are two main groups of tests that we can do, right? We can either do a theory-specific test or what I would call a theory-agnostic test. So theory-specific tests can be more sensitive. We can include more assumptions from the theory, more physical information. And sometimes we have new opportunities to test or constrain a specific theory. So for example, I started grad school in 2019. In 2021, there was a specific quantity in this theory called Einstein ether theory that was calculated for the first time that allowed you to write down the gravitational wave for neutron stars. We'd never been able to do that before. And so now we had a new opportunity. We can calculate the gravitational wave for neutron stars in this theory, and we have neutron star data, right, from the 2017 event. So now we have a new opportunity to test that theory against real observational data. So that would be a prime example of where a theory-specific test might be nice, right? Because we have the waveform, we can see how different parts of the waveform are related to each other, and we can try to pull something out of the data. Alternatively, theory-agnostic tests are really nice because they allow us to constrain more than one theory at a time, right? I personally don't want to be going through that zoo graphic and checking them off one by one, right? It would be really nice if we could come up with some test that would allow us to rule out a bunch of them at once, right? Or if we find some kind of deviation from GR, it could tell us like what direction to go in, right? So let me give you a couple of examples of theory-agnostic tests. First of all, there's the PPE framework. We're going to go into this in a little more detail over the next couple slides, but this gives you sort of a mathematical framework to handle the gravitational wave in a theory-agnostic way. Or you can do things like searching for a unique signature of modified theories. And this doesn't always require you to write out the full waveform. Sometimes you can do it in a geometric way, like we're going to see with polarizations later. Right, so a good example of this is like additional polarizations. Those definitely don't exist in GR, or a modified propagation speed that wouldn't be happening in GR. If we saw something like that in the data, that would be an indication that, you know, there's something else we need to go look for. Okay. So a little bit of detail about the PPE framework. PPE stands for Parametrized Post-Einsteinian. And this framework was developed by Nico Yunis and Franz Pretorius back in 2009. The basic idea is that the modifications to GR must be small, right? We've been testing this thing for a long time. We haven't found anything yet. So probably any modifications to GR, if they exist, are small. So let's characterize these modifications by adding a small term to both the amplitude and the phase of our wave. Okay, so that's what we have here. We have this small alpha PPE. Oh, it's not the same. Here we go. We have a small alpha PPE term and a beta PPE term, and then this U2 factor is like pi MF, and the A or B on that controls the order at which this deviation enters, right? And so usually we search for deviations order by order. For instance, this is what's done in the LVK test of GR papers. And actually, one of those came out last week, so you should go look at it. That's cool. They just released the test of GR paper with GWTC5. This is the latest ground-based catalog going all the way up through observing run 4B. But here we have an example where they looked for phase deviation at different orders and found everything was consistent with GR, but two different levels, right? Two different orders of magnitude at different orders. All right. Okay, so that's sort of an example of a PPE type test. We could also do something like searching for one of these signatures of a beyond GR theory, like additional polarizations, right? So because GR only has two polarizations, detecting any additional polarization conclusively would be definitive evidence of new physics, right? I think that makes these a very interesting thing to search for. So let's go over what they look like just briefly. So as we talked about last Monday, there are only two polarizations in GR. These are both transverse traceless tensor modes. And they propagate with some speed VT, which is the speed of light in GR, right? Okay. So colloquially, these are referred to as plus and cross modes. We already looked at these animations last week, but they're kind of fun. The only thing I want to draw your attention to, if you can actually see them move, if not, you can look at them later on GitHub, but you can see if you track the motion of one of these rings that they're not moving at all along the direction of propagation, right? So all distortion is entirely transverse to the direction of propagation. And if you were to rotate one of these modes by 45 degrees, you would recover the other. Okay. All right, so that's the case in GR. But in some modified theories of gravity, we can have up to 4 additional polarizations. So we can have 2 vectors or 2 scalars or 2 scalars. Okay, so the additional vector polarizations, come on, maybe we just preload, there we go, okay. So these polarizations are interesting because they're no longer entirely transverse to the direction of propagation, but they have a component of distortion along the direction of propagation as well. So the labels X and Y here refer to the plane of motion for each of these polarizations when a wave is propagating in the Z direction. Again, I think animations make this easier to understand, although they're a little glitchy on the screen. So for a wave propagating out of the screen, we can see that the X mode causes no distortion in the Y direction, only from left to right and along this tube. And then conversely, the Y mode causes no distortion in the X direction, only up and down and along the tube. And if we were to rotate by 90 degrees, we could turn one of these polarizations into the other. Finally, we can have 2 scalar polarizations. These 2 polarizations are referred to as the breathing and longitudinal modes because the first one makes a ring of particles oscillate in and out in the plane perpendicular to the wave propagation as if this ring were breathing. And the second is entirely a longitudinal mode, causing a distortion only along the direction of propagation. And these 2 are a little different from the previous 4 examples in that we can't rotate one into the other by rotating around the axis of propagation. In fact, if I rotate around the axis of propagation, these modes look unchanged. That's kind of cool. One thing to be aware of when you're trying to find a theory that has additional polarizations is that just because it has extra field content does not necessarily mean it has additional polarizations. A lot of people make the mistake of assuming that is true, and it is not necessarily. Oh, come on. Sorry, guys. This is behind me. All right. So this is a nice graphic from a review paper from back in 2015, where they lay out a bunch of different possible modified theories of gravity and explicitly describe the field content, what new fields are there in that theory. And this is a great graphic because it also shows you like what other assumptions are broken, right? For instance, we can see here the Lorentz symmetry is good in most of these theories, but not in these couple, right? So that's kind of a useful thing for looking at what theories might break a particular assumption too. Unfortunately, as far as I know, there is no graphic that exists, no table, no summary that lists out what polarizations are active in different theories, because there's a lot of work that needs to go into figuring out what polarizations are there in a given theory. You basically have to go through all of the equations. Yeah, so if anyone knows of a list like that, please let me know. Been searching for one for a couple of years now. Yeah. Oh, well posed is really useful for people doing numerical relativity. They want to make sure that the equations are well posed so they can solve them on a computer. Yeah. All right, so one example of a theory that could potentially generate all 6 polarizations is Einstein ether theory. Like I said, this is the theory that I worked on in grad school. And this is the animation of all of those polarizations together, which is just a little bit trippy to watch. So I would recommend checking that out when you can actually see it and it's not glitching so much. Okay, so why this theory? Why is this an interesting theory to study? Well, one way to modify gravity is to break Lorentz invariance. So Lorentz invariance is a general principle that states that the outcome of experiments are independent of the inertial reference frame in which they are performed. However, yeah, and this particular theory is the most general Lorentz violating theory that one can construct by adding a single additional vector field and its derivatives to your action, and it still gives second order field equations. Okay, so basically this is like the simplest theory we can make that breaks this assumption. So it's a nice testing bed for theories that break that assumption. And why do we care about theories that break that assumption? Well, some attempts to unify gravity and quantum mechanics lead to Lorentz violation. So this means that Lorentz violating theories are potentially an interesting class of theories to study. But the reason we're really going to talk about this one today is mainly because it's the one I'm the most familiar with. I'm certainly not saying go off and study this theory, but it's a nice example because it has a lot of weird stuff happening in it, and we can talk about all of the weird stuff. Okay. So let me just briefly show you the action in this theory. This is really the Lagrangian density, but of course we can use that to get the action. That's a mess. There's a lot going on here. So R is just our familiar Ricci scalar in GR. Now we've added this new ether field, U mu. And if you're at all familiar with a congruence of geodesics, we can think of the ether field as a congruence of time-like geodesics, and then all of these other terms are just the expansion, shear, vorticity, and acceleration of those geodesics, which basically describes how they relate to each other. That doesn't matter so much. We have 4 new terms in the action, and because of that, we have 4 coupling constants in this theory. These coupling constants are what basically control the strength of the modification, like how much do these new terms matter, okay? And so if those coupling constants go to 0, we recover GR, and this means that constraining the coupling constants is going to constrain the theory. And that's going to be our goal as we try to test this theory. We're going to be trying to constrain the coupling constants. Okay. All right. So I don't expect you to understand these. I just want to flash them to show that things get more complicated when we go to beyond GR theories, right? So to get to the field equations in this theory, we need to vary the action with respect to the metric, but also with respect to the ether field and this funny lambda term from the previous page, the Lagrange multiplier. And now our Einstein field equations have this extra term in them, which is some complicated function that depends on the ether field and the coupling constants in this theory. And in addition, we now have like an extra set of equations that we need to solve when we vary with respect to the ether field, which then depends on these complicated terms. So things can get very messy very quickly. There are already a lot of constraints placed on this theory from the many, many different tests of GR that we've done before, and also purely looking at some of the math in this particular theory summarized in that paper at the top. But the point here is that, like, if you want to look at a specific modified theory of gravity, you kind of need to check in a bunch of places to see what's already ruled out, right? We don't want to be exploring a part of the parameter space that's already ruled out by something else. And I also want to draw your attention to this particular constraint. So because there was a joint detection of a gravitational wave and a gamma ray burst from the 2017 binary neutron star event, we are fairly confident the speed of propagation of the tensor modes of gravitational waves is basically the speed of light, okay? And that is going to be really important for this particular theory, because if we look at what the speeds of those different polarizations are in this theory, we can see for this particular theory, they're complicated functions of the coupling constants. And in the case that the speed of the tensor mode there goes at the speed of light, that CT squared should be 1. So C sigma basically needs to be 0. So that's great, because that took us from 4 coupling constants to 3. Things got a little simpler all of the math gets a little simpler when you do that, but this sort of relates back to the question that Levi asked last week, where if we look at something like CV squared, it's a ratio of coupling constants, right? So both of those can be really small, but if their ratio is not really small, you can still have large, large terms in this theory, or large effects. Okay. That's what the gravitational waves look like in this theory. Again, very messy, functions of the coupling constants. And I bring this up mostly to say that it's great if we don't have to work with these. So let's look at a theory agnostic way we can write down the waveform. That's a little better. So the PPE framework, the original paper was in 2009. It was later extended to all polarizations in 2012. So here's what that looks like, where you have like a small amplitude alpha n multiplied by your angular pattern function. So that's like your detector's response to a particular polarization, Fn. And then we have some phase modification as well. And then this was later extended to theories where those polarizations can have different propagation speeds. Right, so you could use something like this instead of the complicated waveform I showed on the previous slide, and then you'd be able to test for multiple theories at the same time. Okay, we're getting close to the end here. Oh, yeah.
From the detection of gravitational waves, the way you use it, right, like with our interferometers, are we able to decouple this polarization from the plus cross?
Through geometry. So because they distort the space-time like geometrically in a different way, they're not going to show up in your detector in the same way as the plus and cross. So if we go back to these animations, for instance, if I had an L-shaped ground-based detector, for instance, and I stuck it in the middle of that ring of test particles, it would see the plus and cross, but it wouldn't see the longitudinal mode, right? Because the longitudinal mode is entirely along the direction of propagation. Ground-based detectors measure the change in lengths of the arms, like how, if they need the lengths of the arms to be different, right? So it's not going to see, say, a longitudinal mode. So if I have a network of detectors, and we're going to talk about this in a minute, then I can start to disentangle them. Right. Okay. I think it's worth mentioning, because we've been talking about theories where I'm allowing these polarizations to propagate at different speeds. What speeds are still allowed? So let's talk a little bit about the current propagation speed constraints. So if the speed of your additional polarization, or if the speed of your gravitational wave is traveling less than the speed of light, then massive particles would be able to travel faster than the gravitational wave, and this would produce a gravitational Cherenkov type radiation. But we don't see that in nature. So high energy cosmic ray observations rule out this Cherenkov radiation, and that implies that any gravitational waves should be traveling at or faster than the speed of light. Yeah, that's weird. Yeah.
When you say like gravitational Cherenkov type radiation,
Yeah.
can you go into more detail of what that looks like?
Not without doing a lot of math. The papers here cover it more. I think it's best to think about this as an analogy with like electromagnetic Cherenkov radiation, right? Where if you're going faster than a particular speed, you're like losing energy through that Cherenkov radiation process. And the point here is that like if your gravitational waves were going slower than the speed of light, you could have really fast particles going faster than that, and then they would have this sort of same energy loss. Yeah, the particles would be losing energy. The particles would be losing energy because they're able to travel faster than the gravitational waves. It's a little weird. That's fine, yeah. Okay. So presumably any gravitational wave should be traveling at or faster than the speed of light. And then, like we said before, we have this nice constraint on the speed of the tensor mode. So those are probably going at the speed of light. And if you put that together, any additional polarizations should arrive with or before your tensor modes. And this can be dramatic. This effect can be quite dramatic. Even a tiny difference in speed can build up over large distances. So for a particular example, let's say we had a source that was 100 megaparsecs from our detector that emitted a tensor polarization propagating at the speed of light in blue and a scalar polarization propagating just a little bit faster in green here. Even that tiny difference is enough for the scalar polarization to arrive outside the standard detection window that ground-based detectors look at. If we want to make this example a little more extreme, if the scalar mode were propagating at a speed different from c by order 10 to the minus 8 instead of 10 to the minus 13, the difference in arrival times could be as much as 10 years, which is about as long as we've been detecting gravitational waves with ground-based detectors. So that's kind of wild. This is incredibly important because it physically motivates searches for isolated scalar or vector modes. And I think it's also a pretty compelling reason to think that we haven't conclusively ruled out additional polarizations with ground-based detectors yet. Okay. So another theory-agnostic way that we can search for additional polarizations involves null streams, and this gets back to sort of that geometric argument that we were talking about before. So null streams were introduced back in 1989 as a way to separate signals from noise in a detector network. The basic idea is to construct linear combinations of data that contain no gravitational wave signal. This was first done for just the plus and cross modes of GR, but then was later extended to all other polarizations. So with this method, we can create data sets that have no component of a certain polarization by projecting the data to a direction orthogonal to the direction defined by the angular pattern function for that particular polarization mode. So for example, a data stream which is orthogonal to the plane of the plus and cross modes would be a GR null stream, or should contain no signal if GR is the true theory of gravity. Okay. Any detection in the null stream would indicate a deviation from GR. This provides a sort of indirect way to search for and potentially rule out additional polarizations. However, there are two major problems with this method, which I'm going to cover in a little bit more detail very quickly. Okay, so the first problem with null streams is that the number of null streams that one can construct depends on the number of detectors with different orientations in the detector network. And here I'm talking specifically about ground-based detectors. Because this is all about geometry and the projection of signals, detectors that are co-aligned don't give us any new information, or in other words, don't help us eliminate any of the degrees of freedom. So we would need 3 detectors to be able to construct one GR null stream because GR contains 2 polarizations. This null stream would contain some mix of the additional polarizations, and then with more than 5 detectors, one could construct complete null streams, meaning you could combine the data in such a way that all polarizations are projected out. Okay. All right, so armed with that information, let's look at the current status of the ground-based gravitational wave detector network. This graphic shows the locations and rough orientations of the 4 gravitational wave detectors that have been constructed so far. So we've got LIGO Hanford in Washington, LIGO Livingston in Louisiana, Virgo in Italy, and Kagra in Japan. Okay, now you might look at this map and think we have enough detectors to start constructing null streams now. After all, I told you on the last slide that we only need 3 to make one GR null stream, and it looks like we have 4. Unfortunately, for our purposes, the 2 LIGO detectors at Livingston and Hanford are co-aligned. This was done intentionally because before we had detected gravitational waves, we needed to maximize our chances of detection, and this orientation was more sensitive, but this means they only count as one detector when constructing null streams. They're not contributing new polarization information, so we're basically down to 3. Okay, and then if we look at this graphic of observing runs over time, we can see that Kagra hasn't really been observing. There's been some hiccups in getting that started. So, yeah, for the purposes of polarization detection, we're kind of down to 2. Just to give you a little bit of background about how to read this graphic, those are the different detectors there listed vertically. The different observing runs, 01, 02, 03, 04, those are like the times we've been observing, and the number on top of each run tells you how sensitive that particular detector is to a binary neutron star merger, like how far out that merger can be, where you get a single detector signal to noise ratio of 8. Just gives you a way to compare different detectors and compare across different observing runs. And if you look at that a little more carefully and you look at the sensitivity that Virgo is operating at, you can see that it's lower than LIGO was in even 01. So I'm going to say conservatively, we've got like maybe 2 detectors for the purpose of null streams and polarization tests. Yeah. What was the reason for what? Okay. LIGO's basically co-aligned, so we went from 4 to 3. Pagra hasn't really been operating, so we went from 3 to 2. And Virgo's not that sensitive compared to LIGO. So we've got kind of 2. Yeah. Right. Another problem with null streams, ensuring we have enough detectors is just the first problem. But the second problem is that this method would only be effective at constraining additional polarizations that propagate at the same speed. And it is potentially possible that additional polarizations may travel at a different speed. So just because the null stream is empty doesn't mean additional modes don't exist. We can't use this information to rule out additional polarizations when they may have simply arrived at a different time. All of that background was to say, additional polarizations are not yet ruled out. Come on. Oh, good. Well, that was the last slide. Here we go. Additional polarizations are not yet ruled out, and PTAs are really uniquely positioned to do something about this. Because there are so many pulsars in the network, because the geometry of this detector is different, and because of continuous wave sources that might be there in the data, PTAs have some seriously unique advantages over ground-based detectors for this particular test of beyond GR signatures. So yeah, that's it. I'm a little bit so. Thanks. Yeah.
How polarizations because the speed is not based on fundamental symmetry.
It does happen in theories that break some fundamental symmetry. So in the particular theory we talked about, Einstein ether theory, you're breaking Lorentz invariance.
That brings conservation of energy and memory.
No. So just because you have Lorentz violation doesn't mean necessarily that other things break. Does that answer your question? Yeah, kind of. We can talk about it more after if you want. Yeah. Yeah.
I have 2 questions for you.
Mhm.
When we're drafting a new theory of extension to GR, what observational and experimental things outside of quantum gravity inspire the direction of that new theory goes?
Oh, lots of things. Pick your favorite open question. And somebody's probably tried a modified theory to fix it. Some people try to propose beyond GR theories to explain dark matter. Sometimes they're proposed to explain like inflationary cosmology. Yeah, there are lots of different reasons, which I am not necessarily an expert in because I don't construct these theories, I just test them.
What makes you find Einstein?
Specifically trying to construct a theory that breaks Lorentz symmetry. Yeah. Oh, so they were looking for basically they were sitting here going, how can we break Lorentz invariance? And they realized the easiest way to do that was to add one vector field. And when you do that, you get all of these extra terms in your action. Like that was the easiest way to do it. And so they ran with that and said, like, what are the consequences of this? Yeah, I'm not by any means saying this is probably the true theory of nature. It's just a good thing to test.
Second question about Einstein.
Yeah.
You said the constraining coupling constants is how you construct the theory.
Mhm.
What experiments is needed to do that?
Oh, okay. Lots of different experiments can constrain the coupling constants in different ways, right? So if we look back at this graphic, we get some from theory, right? So for instance, we need the speed of propagation of the gravitational waves to be positive so that we don't get any what are called ghosts in the theory. You need the energy of those waves to be positive, which puts other constraints on the coupling constants. They have to have certain values so that the energy of the waves turns out to be positive. Those are more like theoretical constraints. You can also get experimental constraints, right? So we had that observation of the 2017 merger that gave us this constraint on the speed of propagation, which because of the way those speeds are written down directly implies a constraint on C sigma, right? There are other, we talked about that gravitational Cherenkov radiation argument. There are also solar system experiments that place constraints on the preferred frame post-Newtonian parameters. Long name, but that's what those alpha 1 and alpha 2 are. And you can write those down in terms of the coupling constants. So you can take this constraint on alpha 1 and alpha 2 and turn it into a constraint on Einstein ether coupling constants, right? And the Clifford-Will Living Relativity Review from 2014 that I reference here, and way back, I think on this slide, yeah, goes through a list of like solar system tests that place a bunch of constraints on these post-Newtonian parameters that were used to rule out a whole bunch of modified theories of gravity throughout the 70s and 80s. I think in Nico and Javi's paper, they basically joke that it cured an outbreak of modified theories in the 80s. Yeah.
Any more questions for now? No, it's zero. So only question. I think we can take a 15-minute break and then come back sort of at 25 past the hour, and we'll have an interactive tutorial from David Wright, who's going to teach us about PTA, how we actually quickly test some of the new physics signals and just do quick analysis with PTA data using this nice interactive. Okay. Yeah, great. All right, so Dave's already here. Maybe if there's something in particular they should do before you start, Dave, just put that on the Slack. But for now, we're going to take a 15-minute break. Okay, just as a note for the Zoom recording, we're going on to a different Zoom channel at the moment because we're having some sharing problems. So we'll probably stop sharing on this Zoom and stop sharing on YouTube for now, for Dave's tutorial, and we'll go on to this other Zoom channel.